Hello everyone and welcome to the Chapter 2 Nonlinear Functions Test Review. We have our test coming up and we're going to be going over everything from Chapter 2 from nonlinear functions with rational functions, polynomial functions, radical functions. You can see anything on this test. If it's been covered in class, you could see it on this test. So let's get right into it. So question 1, what is the horizontal asymptote of this function? So there were a couple things you wanted to remember with horizontal asymptotes. And the thing you really wanted to look at was that exponent. So I have x squared and x squared. And so when those exponents are the same, you just divide the coefficient. So this one's going to be 1 over 1. And the equation is going to be y equal to 1. Remember, if the denominator is greater, so if we had like x squared over x cubed in my denominator, then it would be y equal to 0. And then if I had something like where the numerator was larger, so like x cubed over x squared, then we wouldn't have a horizontal asymptote for that function. Moving on to question number 2, we want to solve this radical function. So I see cube root here, and I'm going to want to cube both sides. So let's cube both sides, put that in parentheses. So I have 7r plus 5 is equal to negative 3 cubed. That gets me negative 27. Subtract 5 on both sides, so negative 32 is equal to 7r. And so r is going to be equal to negative 32 over 7. If that could get simplified, then I would simplify it, but this one cannot be simplified, so I'm all good to go. Moving on to question 3, what is the end behavior of the graph here? So end behavior, we're going to be looking at a couple things. First is going to be that leading coefficient, and the second thing we're going to look at is that exponent here. So I have the leading coefficient. We want to know, is it positive or negative? So we have a positive leading coefficient. And then for the exponent, we want to know if it's even or odd. So this one is going to be odd. So something that has a positive and odd function, that's just a basic cubic function. So let me sketch that out right here. Just that basic cubic function. And what I can see is the end behavior on the right side is going up and the end behavior on the left side is going down. So let's write that out. The limit of f of x as x approaches negative infinity. So that means our left side is going to be negative infinity because it's going down. The y values keep going decreasing. And then on the right side, the limit of f of x as x approaches positive infinity. So this to me says, all right, what's happening on the right side of the function, and the y values, the function keeps increasing to positive infinity. So that's going to be the end behavior of this graph. All right, determine any removable discontinuities and vertical asymptotes of this function. So what I noticed first is that the numerator is not factored right now, so let's factor that real quick. And what I have with x squared minus 1 is a difference of squares. So let's write that out as x plus 1 and x minus 1. Now in my denominator, I have x minus 1 and x plus 2. So the first thing that I notice is that these x minus 1s in the numerator and denominator are the same. So those divide out. And what I want to do with that is set that equal to 0. So x minus 1 equals 0. And what I'm doing with this is it's going to give me removable discontinuities. So x equals 1. But it's not an equation for a removable discontinuity. What you're looking for is going to be a point of removable discontinuity, a hole in the graph. So what we're going to do with this 1 is substitute it back into this function with the x minus 1s taken out. So y equals 1 plus 1 over 1 plus 2. And that'll get me 2 over 3. So that'll get me the y values. So we have a hole or a removable discontinuity at 1, 2 thirds. And it's going to be that equation right there. And moving on to the vertical asymptotes are going to be what's left over in the denominator. So this x plus 2 right there. I'm going to take this x plus 2, set that equal to 0, and my vertical asymptote, let me just abbreviate that right there. I have a vertical asymptote, set this equal to 0, x equals negative 2, and my vertical asymptote is going to be that equation, x equals negative 2. So here in this equation, we want to solve for the variable x. So let's get right into it. The thing we want to do first is factor anything that can be factored. And what I can factor is this denominator over here. So let's do that. X plus 4, x minus 1 over x plus 2 equals x plus 8 over x times x plus 2. All right, so what I notice after factoring that denominator is these two fractions on the left are missing a couple of things. So we just need to add that in there real quick. So what I'm going to multiply this first equation is going to be by x plus 2 over x plus 2. And the second fraction I'm going to multiply by x on x. I don't need to multiply the fraction on the right by anything because this actually comes out to be the lowest common, or the greatest common factor between everything. So let's see. X plus 2 times 2x minus 5, that's going to get me 2x squared. Let's see, minus 5x plus 4x minus 10 over x and x plus 2 plus 4x squared minus x over x and x plus 2 equals x plus 8 over x plus 2 on the right. So what happens with all of these denominators is basically I can just multiply everything by x times x plus 2, and all those denominators are going to factor out. Sorry, not factor out, they're going to divide out. So what I'm left with is that numerator. Let me write it over here. So 2x squared minus 5x plus 4x minus 10 plus 4x squared minus x equals x plus 8. All right, so let's combine any terms that we have that are alike. So I have 6x squared minus 5 plus 4, that's negative 1, minus 1, that's minus 2x, minus 10 equals x plus 8. And since I have a quadratic, I'm going to set this equal to 0. So 6x squared, subtract an x, so minus 3x. And subtract 8 minus 18 equals 0. What I can see is that I can divide everything by 3. So let's go ahead and do that to make this a little bit simpler. 2x squared minus x, minus 6 equals 0. And I need to, let's see if this can get factored. So 2 times negative 6 gets me negative 12. And let's see, I need to make a negative 1 for the b term right there. So I could use negative 4 and positive 3. But since my a term is 2, I need to divide both of those by 2 and simplify. So this first one simplifies to be negative 2. So now that I have the factors, the first factor would be x minus 2, followed by the second factor, 2x plus 3, equals 0. And I can set both of these factors equal to 0 now. So I get x equal to 2. And x equal to negative 3 halves. What you're going to want to do with this is check the denominators really and see if anything comes out that shouldn't come out if you're dividing by 0 anywhere. And what I notice is I'm not dividing by 0 in any of these denominators, so both of these are going to be the final answer. All right. Going on to question 6, we need to divide using synthetic division. So with synthetic division, you just take this factor x minus 2 and set that equal to 0. So I'm going to get x equal to 2 right there. Put that in the corner and you set up your synthetic division with the coefficients 6, negative 12, 0, 1, negative 12. We need that 0 here because we're missing that quadratic term. Bring the 6 down. 2 times 6 is 12, so negative 12 plus 12 is 0, 0, 0, 0, 1 plus 0 is 1, 2 times 1 is 2, and I get negative 10 at the end. So I just start writing this with 1 degree less from where I started. So I have 6x cubed, 0x squared, 0x plus 1, and then minus 10 on x minus 2. And that's going to be our final answer here. All right, here we want to see what is the solution set to 3x plus 2 times x minus 4 greater than 0. So I want to see where is this function going to be greater than 0. So in order to do this, we're first finding the zeros of this function. So my zeros would be negative 2 divided by 3, negative 2/3, and x minus 4 equal to 0. That gets me x equal to 4. And all I need to do is make my handy dandy sign chart. So I make my sign chart here. I'm going to put negative 2/3 on this side, and I'm going to put 4 to the right. And you just want to test these test intervals in that factored form that we have and figure out where is it greater than 0. So greater than 0 on a number line, we're thinking about positive numbers. Since we're thinking about positive numbers, we want to see where is the sign coming out to be positive. So the first thing I'm going to do is I'm going to substitute a value to the left of negative 2/3, probably something like negative 100. Anything to the left is fine. So negative 100 plus 2. So negative 100 times 3 gets me negative 300 plus 2. That's a negative value. And then negative 100 minus 4, that's another negative value. So we're only worried about the signs, not the actual values. And then a negative times a negative will always result in a positive. Anything in this test interval will be positive now. Now I'm going to check 0 in my second test interval. So 0 plus 2, that gets me a positive number, and 0 minus 4 is a negative value. So a positive times a negative will get me a negative value. And checking a value greater than 4, I'm going to use 10. So 3 times 10 is 30 plus 2, a positive number. And 10 minus 4 also gets me another positive number. Positive times a positive is positive values. This is not your final answer. You really want to write the intervals where we're looking at. So those two positive areas. So my area, my solution set is going to be negative infinity to negative 2/3, parentheses. Now, if this was greater than or equal to, then I would change this up to a bracket, but since it's not, I don't need to change it up to a bracket. Union, because I have another spot where it's positive, so union, parentheses 4, comma, infinity. So now you can just read this left to right. And this is going to be your final solution. All right, what is the solution set to 1 plus 5 over x minus 1 greater than or equal to 7/6? All right, so again, I want to set this equation to 0, kind of like what we had done to the last one. I'm going to start this by subtracting 7/6 on both sides. So 1 minus 7/6, that gets me negative 1/6 plus 5 over x minus 1 greater than or equal to 0. But I do need to do a couple things here. I do need to make this as one fraction so we could get everything settled. So I'm going to multiply this first fraction times x minus 1 over x minus 1 so we can have a common denominator. And then the second one I'm going to multiply by 6 over 6, again for that common denominator. So I get negative x plus 1 over 6 times x minus 1 plus 30 over 6 times x minus 1 greater than or equal to 0. All right, so now I can combine these fractions, negative x plus 31 over 6 times x minus 1 greater than or equal to 0. The reason I wrote this as one fraction is because we need the zeros and asymptotes. So zeros are going to happen in the numerator, asymptotes are going to happen in your denominator. So for my asymptote, I'm going to get x minus 1 equal to 0. My asymptote's happening at x equal to 1. I'm going to want to keep track of this. And then for my 0, I have negative x plus 31 equal to 0. or x equal to 31. And I'm going to keep track of that. Now I'm going to move on to my handy dandy sign chart. And then I'll put a 0 right here and positive 31 over there on the right. Again, I'm going to want to find where are these signs coming up to be. That's all I really care about. And we're going to check values in these test intervals. So again, I'm going to pick like negative 100. But I do have this consistent positive with the 6. So I'm going to keep track of that. That is consistently positive in that denominator. And then 100 minus 1, that'll get me a negative. And then in the numerator, I'm going to have negative 100 plus 31. So that's going to be also another negative value. So then what I'm looking at, actually, that's not true. This is going to be a positive value. Do you see why this is going to be positive? This is going to be positive in the numerator because if I'm substituting in negative 100, I have negative 100 right there. And that makes it positive 100. So 100 plus 31 would end up with a positive 100 in the end. All right. And then, so now that I fixed that mistake, in my denominator, I'm getting a negative. In my numerator, I'm positive. So a positive divided by a negative ends up with a negative value. Now I'm looking between 0 and 31. So let's just pick like 2 or something. So negative 2 plus 31 in my numerator, that'll get me a positive divided by a consistent positive right there. And then positive 2 minus 1. So like 2 minus 1, I'm going to end up with a positive as well. Actually, I made a mistake earlier. I wrote 0, but I shouldn't have written 0. What I should have written, if anyone was fixing that for me, what I should have written there is positive 1, because that's the x value that we got for asymptote. I'm going to actually put an a there and a z there. All right, so going back to where I was, if I substitute in like a 5 again, 5 minus 1 gets me positive. So then everything's positive in this case. So I'm positive right there. All right, now moving into values greater than 31. If I substitute in 100, I get negative 100 plus 31, which is a negative value in my numerator. And then in my denominator, I have that consistent positive value right there. And then 100 minus 1, I get a positive. So negative divided by 2 positives, I'm still ending up with a negative. All right, now we need to go back and answer this question. Where is the value greater than or equal to 0? So those are values that are going to be positive in our case again. Greater than 0, numbers greater than 0 are all the positive values. So we know we're looking between 1 and 31, but we can't keep this 1 because this is an asymptote. So we're going to denote that with a parentheses, 1 comma 31, and then we get a bracket on the 31 because that one's a 0. So that's why it's important to label these as you go out to between the 1 and the positive 31. All right, moving on to question number 9, we want to find the polynomial function in least degree with these real coefficients that has the zeros -1, 3, and positive and negative 3i. So as we're going through this, in order to get the answer, we just want to write down the factors. So like x plus 1, x minus 3, x minus 3i, and x plus 3i. Now let's multiply these out. So between the first two factors, I'm going to be getting x squared minus 2x and then minus 3. So that's going to be the first two. And then the second two, I'm going to get x squared plus 9. Now, I'll tell you where I'm getting this plus 9 from. This negative 3i times 3i, that's getting me negative 9i squared. And when I square I get equal to -1. So that's -9 times -1, which is positive 9. Everything else I'm just combining like terms, the inside and the outside are canceling out. Now I have to sit here and I have to multiply all of this out. So you don't want to make a mistake here. You really want to just focus on multiplying everything correctly. So x squared times x squared, that gets me x to the fourth. X squared times 9, that gets me plus 9x squared. Negative 2x times x squared is negative 2x cubed. And negative 2x times 9 is negative 18x. And then negative 3 times x squared is minus 3x squared. And then negative 3 times 9 is negative 27. And from here, we just need to combine whatever like terms we have for our final answer. X to the fourth minus 2x cubed. Then 9x squared minus 3x squared, that gets me plus 6x squared. Minus 18x minus 27. And that's going to be our final answer there. There are multiple solutions to this. You can multiply this by 2 times 3 by negative 1. But either way, the zeros are going to come out no matter what. So here in question 10, we need to determine any removable discontinuities and vertical asymptotes, just like a similar question that we had earlier. So we're going to do it just like that first by identifying any removable discontinuities. And that's going to be the parts that are the same, that x minus 3 here. So I'm going to set x minus 3 equal to 0 and get x equal to 3. And I'm going to substitute that in with the rest that I have. So 3 plus 1 over 3 plus 2, which is going to get me 4 over 5. So I have a removable discontinuity or a hole. I have a removable discontinuity at 3,4 fifths. Now moving on, the vertical asymptotes are going to be everything that we have left over. So that x plus 2, so I have a vertical asymptote when x plus 2 equals 0, and I'm going to get x equal to negative 2. And that vertical asymptote is going to be this equation because it's a vertical line at negative 2. All right, here, this is a definition question. We want to fill in the blank. What indicate where the graph of a function changes from increasing to decreasing and vice versa? So where a graph is changing from increasing to decreasing or vice versa, so decreasing to increasing. So what do we call those points? And those are a couple words you can use. Turning points. Turning points are good. And that's clearly what they are, but if you wanted to, something good to think about, you could also call those critical points as well. But turning points is going to be a more accurate definition about what's happening here. All right, here in this question, we want to solve this rational equation. So I look in the denominators and I see that this first fraction, this x over 1, is not having this x minus 1 happening. So I need to make it have an x minus 1. So I'm going to multiply it by x minus 1 over x minus 1. Let me just write out everything. All right, so I'm going to distribute that x squared minus x over x minus 1 plus x over x minus 1 equals 3x minus 2 over x minus 1. Now all I need to do is get rid of all the denominators. If I'm multiplying everything by x minus 1, all the denominators divide out. So I'm left with what's in the numerator. X squared minus x plus x equals 3x minus 2. These x's subtract out, they cancel out. So I have x squared, subtract 3x, and add 2. And that equals 0. Now this can be factored. We can factor this and say, let's see, we can get x minus 2 and x minus 1 equal to 0. Now we need to just solve for both of those. X equals 2 and x equals 1. That's called the zero product property. But I do want to take a look at these values because if I think about this x equal 1 right here, in the denominators I'm getting 1 minus 1. Do you see that? And what's happening is I'm getting like 3x minus 2 over 0. Or really we're getting something like 3 minus 2 over 0. If you think back early on when you were learning division, you cannot divide things into 0 groups. So this would actually be an extraneous solution. In our case, x equal 2 would be the only solution to this equation. All right, now we want to solve the inequality. Where is that greater than negative 16? The best way to do this is set it equal to 0. So x squared minus 2x minus 15 plus 16. That's going to get me plus 1 greater than or equal to 0. Sorry, not greater than or equal to, just greater than. And now I want to factor this, and I can factor this. I can factor this x plus 1. Sorry, I lied. This can be factored as x minus 1 times x minus 1 or x minus 1 squared. So solving for this, we end up with 1, 0, x equal to positive 1. And now we bring out that handy dandy sign chart. So I'm going to put 1 right here. And I want to check for values on the left side. So values, actually, let's look at values that are to the left of 0, like 0. So 0 minus 1 squared, I'm going to end up with a positive value. Because I end up with a negative squared, but that's always going to be positive. And then on the right side of 1, I end up with like 100 minus 1, so that would be like a positive squared. And then if I square a positive, I end up with a positive value again. So where is this going to be greater than negative 16? Well, it seems like it's going to be greater than everywhere. But right here at 1, it's equal to 0, so we're not going to include that. So we just need to include the positive parts. So negative infinity to 1. Union 1 to infinity. We had to take out that 0 there. All right, now we want to solve the inequality here. I'm going to first start by setting this equal to 0. So 1 over x minus 1 over x plus 5 is going to be greater than 0. And then I need to create a common denominator. So this first one, I need to multiply by x plus 5 on x plus 5. And the second one, I need to multiply by x over x. I distribute everything. I get x plus 5 over x times x plus 5 minus x over x times x plus 5 greater than 0. I want to combine these, so I end up with 5 over x times x plus 5 greater than 0. Now I do have two vertical asymptotes. I have a vertical asymptote here at x equal to 0 and x equal to negative 5. So let's put those down in our handy dandy sign charts. So negative 5 there and 0 there. Let's work with these values that I have in this rational function at the end. So I want to see again, where is this positive? So that I can see, all right, what do I need to see from my sign chart where everything comes out to be a positive sign? So if I substitute values less than negative 5, like negative 100, I end up with a negative times a negative, which means this entire fraction ends up being positive. Now moving on to this center area, if I choose a value like negative 2, I have a positive in my numerator, a negative, and then a negative times a positive in my denominator. So what happens is this entire part becomes negative. And then on the right side of the equation, if I substitute in like 100, so positive in my numerator, I'll have a positive times a positive, which makes this entire thing positive. And what we see here is that we want to figure out where this is positive. We're going from negative infinity to negative 5. Union 0 comma positive infinity. We're just really reading the numbers left to right on a number line. And finally, we want to solve this polynomial function to find the exact values of all zeros. Now I give you guys the graph to help here, but it seems like a pretty large function. But what I notice is that this has like this cubic kind of behavior through negative 2. So what that's telling me is that I have multiplicity happening here at negative 2. So since I have this multiplicity, I'm going to use synthetic division 3 times because I have multiplicity of 3 times at -2. So I'm going to use -2 and I'm going to divide 3 times. So 1, 6, 21, 62, 108, and 72. So let's do this. 1, -2, that's going to get me 4. And then I get -8, 21 minus 8, that's going to be 13. -2 times 13 is -26. 62 minus 26, let's see, 5, 12, 6, so 36. -2 times 36 is -72. And 108 minus 72, that's going to get me 10, 3. And then 18, or 8 minus 2, that's going to be 6. So -2 times 36 is -72, and that's a 0. So I know I should be getting 0 here, but that takes care of one multiplicity. I have 2 more to go. So -2 now, using our resulting numbers, 1, 4, 13, 36, and 36. Oh, we got 36 twice there. All right, so then I bring the 1 down. I get -2. 4 minus 2 is 2. -4, 13 minus 4 is 9. -2 and 18. -2 and 9 make -18. 36 minus 18 is 18. And 18 times -2 is -36. So 0 now. I have 1 more to go. I'll do it right here. -2. So I have -2, and then the results 1, 2, 9, and 18. Doing that division now, 1, -2, 0. -2 times 0 is 0, bring the 9 down. And -2 times 9 is -18. So now my result is x squared plus 9 equals 0. All right, so here we are. We need to solve for x. So we're going to solve for x right here by subtracting 9 on both sides. So x squared equals -9. And then all we need to do is take that square root on both sides. So x equals, remember when you take that square root of a value, you end up with a positive and a negative value. So the square root of 9 is 3, but the square root of -1, that -1 getting multiplied right there, is I, that imaginary number. So we end up with 5 zeros. We end up with x equal to -2 with a multiplicity of 3, because that's happening 3 times. So x equals -2, -2, and -2. And then we get x equal to 3i and x equal to -3i for our final answers. All right, that's going to cut it for the Chapter 2 test review. These are all the solutions, all worked out for you. Make sure you guys study for your test. I'm Mr. Hernandez, and I'm always here to help.